Hi, we're back with some applications to universal gravitation. This is going to be one of a couple videos that we're going to put together here for you on these topics. I want to start off with this idea of universal gravitation again. When we're talking about universal gravitation from our last video, we said that universal gravitation was the force of gravity is equal to big G m1 m2 over r squared. And I'll do some problems with this in another video, but just using this conceptually for a derivation purpose, let's assume that m1 is the mass of u. I'm just going to say u, a person. And let's say that m2 is the mass of the Earth, m sub e. With that said, we can plug in the values of the force of gravity is equal to big G mu times the mass of the Earth divided by r squared. The distance, r squared, would be the distance between you and the center of the Earth. And we're going to talk about that a little bit more in a few seconds. But when we take a look at this equation, we already have an equation that describes the force of gravity on you. And that equation comes to us from the concept that F equals ma. And so we said that when the acceleration of gravity, or g, is equal to 9.8, we can calculate your weight. And so that means, which is ultimately just a force of gravity here. But what we can say from this is that force is equal to force. And that's always been the case. You could set forces equal to each other. You could set masses equal to each other, solve problems. And so if that's the case, what that means is that in this equation, we have the mass of u times g. The mass of u times g. And setting these two concepts equal to each other, we get the mass of u times g. So this is the mass of u, is equal to big G, the mass of u, times the mass of the Earth divided by r squared. And immediately we can see the mass of u cancels out. And so we get a value that says G is equal to, which we call gravity, 9.8 meters per second squared, is equal to big G, which is that constant, 6.67 times 10 to the negative 11th, times the mass of the Earth divided by the radius squared. And so we have a way of calculating out the gravity that you're experiencing here on Earth. The crazy part about this is that with this information, this equation, we can look at, for example, the moon and figure out its gravity, or if we already know its gravity because we did some experimentation there, we can figure out its mass if we know its radius. And so we can find relationships between gravity, the mass, and the radius squared. When we're talking about gravity is the force that's pulling all objects in. And at the beginning of our solar system, there were blobs of rocks and debris floating around randomly in the solar system. And these rocks and debris eventually collided with each other. And when that happens, we get a more blobbish shape object. Over time, the gravitational forces pull that object into what we call a sphere. And so gravity is pulling the objects together. And so when talking about the gravity of Earth, what we're talking about is the idea that all of the mass, all of the rock and gas and liquid on the planet is attracted to all other mass, gas, and liquid on the planet. And so the center of mass of this, remember our concept of center of mass, being the center of the Earth, is going to be the point in which we measure the mass of the Earth. And so if we are an object on Earth, here you are standing on Earth, we're an object on Earth, it's going to be the distance between you and the center of the Earth that matters, which is going to be 6.37 times 10 to the 6 meters, or 6.38 times 10 to the 6 meters. Depending on where you're measuring from, you could get slightly different values to this. You will hear me use this value, but you will see in some books they use this value. College Board or a problem will provide a value, and in reality, it doesn't really matter if you use 6.37 or 6.38, because in terms of significant figures, usually the hundredth spot is going to cancel out and be within a rounding error margin. Now, the Earth is also spinning on its axis. Okay, there is an axis pole about there's an axis pole, and we are spinning about that axis pole. We are tipped at about 22 degrees to the sun. So if this is the sun over here, we are tipped at a slight angle to that, but we are spinning about that axis. We would call this our North Pole. We would call this our South Pole. I'll get back to the poles and the seasons in a few minutes, but as this Earth is spinning, it is going to need to have a greater centripetal force at the equator than it does at the poles, because there's a greater radius there. And so the inertia of the Earth caused it, I should say, as it was forming, to not be a perfect sphere. It is still a very close sphere, but it's not a perfect sphere. Here are some equations here, and you could see on the screen that we're not talking about a very large difference between 12,756 kilometers and 12,714 kilometers, but it is a little flatter on the top than it is other places. That difference, that radial difference, along with the concept of, and here's just another picture of this showing the radial differences. What you're looking at here is the radius values at the poles, 6,361 kilometers, approximately, a little bit more than that towards the blue side, 6,381 towards the darker red side. And so as you get out towards the equator, it does rise up. You can also see the mountain ranges here that have brought some elevation in. But even with that said, that the Earth is not a perfect sphere, it's also not perfectly homogeneous in its density, because there are places where there are denser rock. There are places where the core is closer to the surface. And so that means that with a change in radius and a change in the density of the rock structure, we are going to see a gravitational change at various points around the Earth. And so here is a map of the gravitational changes, and you could see here that we do get some different gravities. A better map of this is a very flat map, and it does provide a real nice guideline to help you see what's going on. But we're looking at Europe and Africa having some high gravities there. But when we go over to this other map, this is on Wikipedia, we can see here specifically what's happening in the United States in that right picture. And we can see that out west, we are having a higher gravitational field out near the Rocky Mountain Range. In fact, as you head down the Rockies, you can see that down in the very southern parts, actually probably those are the northern Andes in South America, we are seeing a very, very high level of gravity. This is measured in milligauls. It can be converted here. You can see that 1 milligaul is equal to 100 1 over 100,000, or 1 times 10 to the negative fifth meters per second squared. So gravity is changing. On top of gravity changing around the Earth as it spins, we also find, again, that gravity throughout the universe is varying because mass is moving. So the gravitational attraction of on our moon by Mars or Venus or another planet is changing because our distances away from them are changing as we are traveling around the sun. The reality is, and here this is a very, very important point, that there is no place in the universe where we have zero gravity. Now, that's going to lead to questions about what's weightlessness, and we're going to talk about that in a little bit later video here, but weightlessness in terms of an astronaut traveling around, but in terms of gravity itself, there is no place in the universe that has zero gravity. We do have places that have very low gravity. So keep that in mind. I hope you, if you have any questions, let us know. Hopefully, you can have the opportunity to look back through this if you do have questions, and you'll be able to find some answers. Thank you, and we'll see you in the next video.